Hello, geometry friends. Today we are going to do some notes on how do you do a two-column proof to prove something is a parallelogram in a two-column proof. Prior to this, we've done two-column proofs where I tell you something is a parallelogram, there we go, and you use those properties to prove triangles. This time we're going to go the opposite direction and say, hey, that looks like a parallelogram, but is it a parallelogram? I'm not sure. Okay. So there are a couple different ways to prove that something is a parallelogram. And if you can get to a point where you have any of them true, any of these different ways, then you know you've got a parallelogram, all right? So we are working on this sheet. Hopefully you have it in front of you. And I'm going to get started. Way number one. The most quote unquote obvious way to prove that something is a parallelogram is to prove that it has parallelism going around. Both pairs of opposite sides are parallel. So if you can get to a point where you know both pairs of opposite sides are parallel, then you know it's a parallelogram. Okay, so if I'm given quadrilateral EFGH with EF equal to GH and EH equal to GF, prove that it's a parallelogram. All right, so the goal here is to get both pairs of opposite sides parallel. Well, they told me that both pairs of opposite sides were congruent, so I'm going to write that down as a given. And then I'm going to think, how do I prove things are parallel? Well, I prove that things are parallel if I can find some congruent alternate interiors. So that's my goal here, is to find some congruent alternate interiors. Well, once I know that those sides are congruent, I also know that these two triangles that are present share side FH. So FH is congruent to itself by the reflexive property. And then I realize that all the sides are marked in both of those triangles. So those two triangles are going to be congruent by SSS. Okay, fine. How does that help me get angles? Well, once you know that triangles are congruent, you can use Cpctc to prove all their angles congruent. So I can come in here and say that 1 equals 2 and 3 equals 4 by Cpctc. And then I can say, wait a second, if 1 equals 2, those are alternate interiors, which would make EF parallel to GH. And if 3 equals 4, that's another pair of alternate interiors, which would make EH parallel to FG. So EF and GH are parallel, EH and GF are parallel because if alternate interior angles are congruent, then the lines must have been parallel. And then last but not least, EFGH is a parallelogram because both pairs of opposite sides are parallel. Okay, cool. Another way to prove something is a parallelogram. Oh, you know what? Before I say that, the reason I started with this proof is because when we did coordinate parallelogram proofs, I said the best way to prove something's a parallelogram in coordinate geometry is to show that both pairs of opposite sides are parallel. That's the quickest. It is one of the ways to prove it in a two-column proof, but it may not be quickest. There are more, and that's why we're going to go into these. All right? So now I'm going to scroll down here. If one pair of opposite sides is both congruent and parallel, then the quadrilateral is a parallelogram. And you may be thinking, well, why do I need a second way? Well, because sometimes when you don't have coordinates, you're only given enough information to talk about one pair of sides, and the other pair is just, floating out there doing whatever it does. All right. So if you can get to a point where you only know something about one pair of sides, but you can prove that that pair is both congruent and parallel, it's a parallelogram. Let me show you. Given that PE is perpendicular to SQ and RF is perpendicular to FQ, SE is congruent to QF, PE is congruent to RF, prove that it's a parallelogram. Okay. This one's a little bit trickier than the last one because the last one, right off the bat, you're thinking, well, this kind of looks like a parallelogram. Opposite sides, they told us, are congruent. In this one, I don't know anything about the outsides. All I know about is the insides. So I'm given all that information, and what I realize once I'm marking this is that I am going to have SAS for these two tiny triangles here. So I'm going to get in here saying, you know what? They talked about perpendicularity, so I know I have some right angles. So angle PES and angle QFR, which are these two, those are going to be right angles because perpendicular lines form right angles. And then for number 3 here, I know that angle PES is congruent to QFR because all right angles are congruent. And once I've shown that the angles are congruent, now I know the triangles are congruent by SAS. So PES is congruent to Q. No, if I said PES, it would be RFQ by SAS. All right, so where does that get me? Well, if I know that those triangles are congruent, I know that side PS is congruent to QR. So that gets me one pair of opposite sides congruent. And then if I want to show that those sides are also parallel, I have to find some alternate interior angles, and I'm going to find them right here. Angle PSC and angle RFQ. Angle 1 and angle 2. Now, why do I know that those green things are congruent? Because the triangles are congruent. By Cpctc, corresponding parts of congruent triangles are congruent, I know that those matching parts are equal. And if 1 equals 2, then I know PS is parallel to QR, because just like the last time, if alternate interior angles are congruent, then the lines are parallel, which means that, so I have this side is congruent and parallel to that other side. Now I know PQRS is a parallelogram because one pair of opposite sides is both congruent and parallel. All right. There are 2 more methods here, okay? 2 more methods. One more method, if both pairs of opposite sides are congruent, then it's a parallelogram, okay? So what if you don't want to have to worry about parallelism because you don't know anything about the angles? You could just say, you know what? Prove that the opposite sides are congruent. Before I start this proof, I'm going to be honest with you and tell you, I kind of lied to you a couple minutes ago, and I made you do a proof the long way. If we scroll back up here to number 1, and I look at these givens, I gave you that EF and GH are equal, and that EH and FG are equal. In this proof, if I had given you all the reasons up front, this proof right here would have been not even a 2-step proof, 2 steps if you include the given, would have been a 2-step proof. So using reason number 3 or question number 3, now that I know that these opposite sides are congruent, I could do step 1, copy out my givens, and step 2, EFGH is a parallelogram because both pairs of opposite sides are congruent. You didn't need to do everything that I did. Now, I did it on purpose because I wanted to show you that if you can get both pairs of opposite sides parallel, it's also a parallelogram. But now that we have this third way, if I can get that both pairs of opposite sides are congruent, then it's a parallelogram too. So if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. I would really like to go through and do this proof with you, but I got to admit, I just realized that there is a typo in it. And rather than have you walk through the typo with me, we're just going to say, if you can get to this point, you know it's a parallelogram. And to keep this video short, I'm going to just do the last part that says if both pairs of opposite angles of a quadrilateral are congruent, then you can also prove it's a parallelogram. And I'm going to just shortly tell you that means, like in this picture, if I could prove that this equals this and that equals that, then I would know that that little inside guy is a parallelogram. And with that, I am done. There are the 4 reasons where a quadrilateral could be a parallelogram: both pairs of opposite sides parallel, both pairs of opposite sides congruent, both pairs of opposite angles are congruent, or one pair of sides is both parallel and congruent. Technically, there's a 5th one that if you can prove the diagonals bisect each other, that works too. But honestly, it's usually easier to prove the other ones. And I'm done. I hope everybody's having a good day. I'm sorry for my typo and the music if you can hear it playing in the background.